Thank you very much for interesting our recent results, which is entitled High-Throughput Detection Circuit based on 2 to the q+1 valued deep neural network. This work is the outcome with the joint research with my students, Mr. Soga and Mr. Crouch and me, Nakahara, from Tokyo Institute of Technology, Japan. So this slide shows the outline of my talk. First, we will talk about the background of my research, and then we will introduce convolutional neural networks, CNN, for computer vision systems, which is higher recognition accuracy. Then we introduce our new technique to mapping the lookup tables technique for the FPGA circuit from training the convolutional neural network. And then we will talk about the lightweight method to compact representation of the neural networks, which is suitable for hardware implementation. And we talk about the binary representation in past. Then we extended it to the ternalized one. So to do this, we use weight sparseness technique, which is eliminated and use weight for convolutional neural networks. And we will extend it to the generally 2 to the q+1 valued representation of such CNN. In that cases, we have the trade-off between the accuracy and the hardware size with respect to the values of the Q. And we will show the experimental results using different number of the Qs, and we will show the hardware implementation results, and we will discuss the trade-off for which value is suitable for LUT mapping methods. And finally, we will conclude on my talk. So there are big demand for the data center. It's requirement a high-speed inference with low power using the deep neural network. It is widely used in classification or intrusion detection tasks in the data center. For example, the embedded systems, including security camera or robotics or some automatic driving systems also demand such higher accuracy with deep neural network. Also, cloud systems is so. So this talk, we are going to the implement of the deep neural network systems for cloud systems. But we have serious problem for cloud system using deep neural network. Typically, deep neural network requires us to massive memory accesses and DSP computations. And to solve it, we propose a combinational circuit representation with lookup table, which is main computation element of the modern FPGAs. And we are going to realize combinational representation systems which satisfy the high speed with flexibility for different types of the networks of the data sets like this. So here we introduce convolutional neural networks, CNN, is widely used in modern computer vision systems using deep neural networks. Then we will introduce this of the lookup table mapping. We are going to convert from the two-dimensional convolutional operation to the one-dimensional one and do mapping to the lookup tables of the FPGAs. So convolutional neural networks, CNN, including the different type of the computation for each layers, one is convolution or pooling or fully connection, and it achieves the higher accuracy than the other machine learning systems. Then it is a main role of modern computer vision systems, but its requirement with huge parameters, and most serious problems is we must accelerated to keep up with the real-time computation. So dominant computation of the CNN is a convolutional operation which occupies the more than 90% of the computation. So suppose that we have trained the weight, which is a kernel typically consisting of 3 times 3 size of the windows. And then we go to the incoming images from X. Then we apply the convolution operation. Then we can compute the next feature maps the neurons. So in that cases, we must accelerate it many of product sum computation like this. So the problem is how to compact representation of the circuit and achieve the high performance and low power computation. So to compact representation of the convolution operation, we introduce this conversion from the two-dimensional typical convolution operation to one-dimensional model. So by rewriting to the two-dimensional computation into the one-dimensional one, we have this typically neural computation model. Then our problem is how to compact and simply circuit representation of this model. So to simply representation, we are going to use lookup table mapping because lookup table is a basic computation element of the FPGA. So if we put on the such computation to lookup table, then we can realize the combination circuit representation on the FPGA. So suppose that we can successfully convert a two-dimensional convolution to one-dimensional one. So one-dimensional representation can be realized of the k square multiplied n inputs and outputs table lookup method. And just look of the tables, then we have the next output of this one. And this is very simple computation and faster computation one. Unfortunately, but we have serious problems for straightforward realization of the LUT mapping method because it's in classical memory size. So typically, lookup table size is the 2 to the qn multiply n multiply number of channels and the number of layers. And let q denotes number of weights, and let n denotes bit precision. And typically, without no consideration, we are widely use 32-bit, and this is dominant for the memory size. And other parameters is relatively smaller than the such values. So this talk, we are going to compact representation of the bit precision n to the binary or ternary representation. So we introduce this lightweight computation method to represent it such huge size of the memory size, including binarized representation. And next one is weight sparseness, so eliminated unused weight. And we extended it to the 2 to the q's +1 valued representation. So +1 denotes it as 0, that eliminates unused weight. And we also represented all the hardware realization. Okay, let's discuss the basic definition of the neural network model. And it computed incoming inputs and trained the weight and multiplied summation and additing the bias. Then we have the neural values. In that case, we apply the activation function. So typically, we use a real function which generates the plus value or zeros. And we convert it to the binary activation, not weight neural network. Because this model, we consider the floating 32 point. This is the same one, originally one. Because after computation of the lookup table. So weight is inserted to the lookup table. So we just only consider the incoming signals and outgoing signals for the binarized one. So this is very suitable for training because fully binary, including weight and occupation, is relatively harder. But lookup table cases, we just considering the binarization for the just incoming signals and outgoing signals. And the next technique we introduce is the weight sparseness or pruning technique to eliminate it and use the weight. So in first our publication discuss the two types of the pruning technique, which is weight edge pruning or neural pruning. And please look these figures. We increase the number of zeros ratio and recombination accuracy for MNIST networks. So typically, we achieve the more than 90% and keep the recombination accuracy. And we introduce internalized one. By applying the pruning technique to the binary neural network, then we can represent it to the -1, +1, and 0 representation. So this is a sparseness binary neural network or ternalized neural network, which is suitable for hardware implementation. We extended to the ternalized neural network to do the q+1-Valued representation. So for example, q equal to 2-bit, so it is a 5 value because -2, -1, 1, 2, and 0. And 0 denotes its cutting the connection between the lookup table, which is suitable for sparseness representation. And next, we convert the two-dimensional convolution to one-dimensional representation by using the Sparse Local Convolution technique. This is unshared weight convolution, and we have different kernels for different location of the inputs. And then we have different types of the inputs that is suitable for the sparseness techniques. And we also introducing the node-wise pruning. So more detailed algorithm is written in my paper. So if you're interested, please look my papers. And this algorithm uniforms the number of connections and apply the pruning technique. And because the maximum size of the lookup table is dependent on the maximum number of inputs, in that case is 8. But we keep the uniform number of inputs of the neural network, then totally memory size is reduced by compared without considering the node-wise one. And we also another technique to decompose the lookup table into smaller one. This is a functional decomposition, and it's partition into smaller number of inputs. And fortunately, so convolution operation is weighted some function. And this is already analyzed by Professor Sasao. And we also apply the functional decomposition after lookup table mapping. Now we talk about the experimental results. So we make the synthesized flow from the trained to the q+1-Valued neural network. And then we optimize with FPGA CAD tools, including functional decomposition or lookup table mapping and bit stream generation with academic CAD tools. And we do the experiments, compare the existing neural networks, and we investigated the number of lookup tables and its accuracy. And we choose the datacenter FPGA, that is Xilinx RVL U200. And we compare with conventional neural network. It reduces number of multiply accumulation operation with considerable accuracy. So by removing sharing, freedom of weights has increasing. As a result, it reduced the number of unnecessary multiply accumulate operations. And we also investigated the trade-off, the number of lookup tables and accuracy by changing the activation bits Q. So our results denote that the Q equal to is the best this is 5-valued, and it achieves a higher recombination accuracy and considerable hardware size compared with Q equals 3 and Q equals 1. And we also compare with existing FPGA implementations published in FCCM. This is top conference at the FPGA 1. And we achieved the higher recombination accuracy, smaller number of lookup tables, and high-speed computation compared with conventional one. This is a summary of my talk. We introduced the lookup table mapping method, and including lightweight computation, including binarized one, sparseness one, and we extended it to the q+1-Valued representation, and achieved higher recombination accuracy and smaller size of the lookup table. And this is summary. And our future work is accuracy improvement. For example, to accuracy increasing more, we will introduce the ensemble method to achieve the more high accuracy. But our serious problem is training tool for huge size model, because our training tool extended it to the conventional neural network is larger one, and the GPU memory is dominant to train the large size of the neural networks. And we are going to develop the next version of the training tool that is suitable for larger data size of the neural network. Okay, that's the end of my presentation. Thank you very much for attention.